Hi, welcome. In this video, we will solve validate binary search tree asked by many companies like Google, Spotify, LinkedIn, Uber, and many others. Now let's check out one more problem binary search trees. Okay, that is a validate binary search tree. Okay, so far we have covered some questions on binary search trees. Okay, now let's check this problem, and here you will get a more insight of what is a validate, what is a binary search tree. Okay, so given a root of the binary tree, determine if it is a valid binary search tree or not. Okay, so let's understand what is a binary search tree is. Okay, so a valid BST is defined as the left subtree of the node contains only nodes with the keys lesser than the nodes key, right? So basically here, this is one node, left node. So the left node value should be lesser than the nodes key, right? This root value 4. So you can see on the left side, the values are lesser, right? If that is a valid binary search tree, right? Here you can see like 1 has a lesser value than 2, right? So on the left side, if the values are lesser, if the root values are lesser, that is a one of the condition of binary search tree. Okay, next condition, the right subtree of a node contains only nodes with keys greater than the nodes key. So basically, let me give you one example. So suppose I have one node and this has one node, this has one node, this has one node, and this has one node, right? This one node, one node, one node, one right node, and then this left node, right? So according to the first condition, the left subtree of a node, basically left subtree, right, of a node. So that means this complete tree. Let me take this marker. This complete tree. Okay, this complete subtree, right? Starting from here, this is complete subtree, right? Left subtree, and this is complete right subtree, right? So they are saying the left subtree of a node contains only nodes with keys lesser than the nodes key. So suppose if we have 9 here, so here all the nodes should have lesser value than the root node, right? And in the right subtree of the node contains only nodes with keys greater than the nodes key. So here on the right subtree, all the nodes should have value greater than 9. So here the values of all the nodes, that is x, should be greater than 9. Here, suppose x, all the values should be lesser than 9, right? So these are the two conditions that I have covered. Now both the left and the right subtree must also be binary search tree, right? So now they are saying both the left and right subtree. That means this left subtree, LST, right? This left subtree will also be a binary search tree. That means again the same thing, right? Again the left subtree of this root node. Basically this left subtree, this should also be work in the same fashion. So basically here all the nodes like this node and this node should have the values lesser than this, right? Okay, and here this is the right subtree, so here the value should be greater than this. Similarly this right subtree, here the values should be lesser than this one, right? Here should be the values greater than this one, right? So let me give you one example of a binary search tree. So we have, right, suppose starting with I am 8, I have one node, that is here 3, right? Then I have 1 here, right? Then 6 here, then 4 here, 7, right? I'm starting here with the 10, right? 10 to 14, and here I have a 30, right? Now let's see. I have 8. So on the left subtree, all the values are lesser than 8. So 1, 3, 6, 4, 7. All the values are lesser than 8. Right. On the right, all the values are greater than 8, 10, 14, 13. Yes, all the values are greater than 8. So here, all the values are lesser than 8. Here, all the values are greater than 8. Right. Now, the left subtree should also be a binary search tree. So here, 1 is lesser than 3, 6 is greater than 3, and all the values on the right should be greater than 3, right? So 6, 4, 7, all the values are greater than 3. Right. Now this right subtree should also be a binary search tree. So 4 lesser than 6, 7 greater than 6. Right. So this is also a valid binary search tree. Right. Here you can see here we have 10 greater than 8. Right. If there is a left node, that should be lesser than 10. Right. But there is not. If there is a right node, should be greater than 10. And yes, 14 is greater than 10. If there is a left node, should be lesser than 14. Yes, 13 lesser than 14. So that is a valid binary search tree. Okay. Now let's check out the examples. So here I have 2 as a root node, the left subtree. So we have left only one node that is lesser than 2. So okay, that's correct. Let me put with green pen, that's correct. And the right node is greater than 2. So that is also correct. And there are no further nodes. So yes, that is a true. So I will return true here. That's why the output is true here. Okay. Now let's check this case. Right. So I have 4 as a root node. On the left on the left side, if there is a subtree, all the nodes should be lesser than that. There is only single node. So 1 that is lesser than 4. Now on the right, here I guess this figure is not like this. This figure is like this because I'm just checking in the input. It is 5, 4, and this one. Yeah. So basically you can see it like this 5, then 1, 4. These are level order traversal. And then I have null, null. So basically this is null, this is null. And then we have 3, 6. Okay. So now let's check this one. So on the left, is the value is lesser than 5? Yes, it is. On the right, the value is greater than 5? Yes. No, that is not. Right. On the right, the values are not greater than 5. So that is a wrong case. That is a wrong case. And that's why I will return false. That's why I will return false. Even if this is a case, even if this is a case of 4 to 5, okay, this is 4, this is 5, right? Even this will also false, right? Here on the left, you can see on the right side, all the values should be greater than 4, but you can see here 5 is greater, okay, 6 is greater, but 3 is not greater, right? So the left, there is the right subtree, it's not a valid binary search tree, okay, so that's why I'm returning false. So I hope you clear with the input and output, basically what we need to do. And now let's see how we are going to solve this problem. Okay. So here I have a valid binary search tree. Okay. So what will be our approach basically? Let's think out it. Let's think of it. So basically we basically do traversal, right? We know from this node I can reach to this node, from this node I can reach to the left, then I can come here, then I can reach to this node, right? That is possible. And we know that I can compare between these two, right? So if I talk about it, I can compare 3 and 10, right? Basically what I can say if there is a left node, so left node value should be lesser than the root node, root dot well, right? I can do this thing and I can say right node value should be greater than the root node, root dot well, right? So I know that I can compare this one, right? And similarly, in the same way, I can move ahead, right? I can compare this two also. So I can compare again the same thing. Left node value should be lesser than the root dot well, and right node value should be greater than the root dot well. Okay, and this will work. But what will happen then? Like if suppose one of the condition is following this one. Let's suppose like they are saying like here the value should be lesser. So here the value should be lesser than 6. So here I have mentioned like what was the thing was given 4. Okay, that is true. Now let's see how I can tweak this. Yeah, let's see. So if I extend further one, okay, if I extend this further one, here I am getting 0, okay, and here I am putting 9, right? So if I apply this logic, right, if I apply this logic that we were trying, that left node value should be lesser than root dot well. So yes, left node value is lesser than the root dot well, and right node value should be greater than root dot well. So yes, right node value is also greater than the root dot well. Okay, that is a validating yes. So it will return me true, but that's a false case. because here 9 is greater than 8. 9 is greater than 8, and we are missing that all the nodes, all the nodes on the left side, all the nodes should be lesser value than 8. Similarly, right here, instead of 7, suppose if I have here, suppose 3 greater than 3 but less than 7. So I'm saying, let's suppose, yeah, we have only 9, right? So if we have here 9, so here this is following this condition, right? This is following this condition, right? 9 should be lesser than 8. Basically, here the node value should be lesser than 8. Okay. So yeah, that is one thing. Also, suppose take one more case here. Now this is 2, right? So 2 is lesser than 8, valid. 2 is lesser than 6, valid. But 2 is not greater than 3. On the right, all the nodes should be greater than 3. So we have 6 greater, we have 9 greater, but 2 is not greater. So basically, what is the hindrance in our logic, that I can check the left node and the right node for the just a tree, like the most recent, I can say, or my recent left node. But if I need to check for all the left nodes, right, this one, this one, this one, then this logic will fail, right? So basically, if I have one node 8, and then I have one 3, right, and then I have one 10, so my logic will work, because if I am looking for a immediate left and immediate right, right? For immediate left, this is working. For immediate right, this is working. So my logic is fine. But I want to check for all the possible of my left subtrees, all the possible my left nodes. Then this will fail, right? This will work for the immediate left. Maybe for this one, this will work. Right? But if I want to compare this one with this node that is at the farthest node or the leaf node, then this will create a problem. So I hope you got the issue, right? This is the very first thing that we should always figure out, that what is the problem? Why I can't go with a simple approach, with my own approach, right? But the problem is that we can't compare the leaf node or the farthest node with our root nodes, right? I should be compare with all my nodes. So what we will do, again, let's take one example. So I will first of all create a binary search tree. So I have this binary search tree 8. Let's create the same 8 with 3, then with the 10, with 1, same valid binary search tree we are creating, right? That is 6. And here I will create 2. Now that is not valid, because here 2 should be not there. The value should be greater than 3. Okay. Here I will make 7. Here I will make 14. Here I will make 30. So what I will do, here I 8, here we have in 8, right? Here there is no condition. So what I will do, my root values should be lies in an interval, right? So for this 8 value can be lies between plus infinity to minus infinity. Can I say my plus infinity to minus infinity, this will lie, right? Plus infinity to minus infinity. Yes, right? I am taking a basically I am finding the two values. I am finding the minimum and maximum, right? Why I'm finding? Because see, for this node needs to be true, for this node needs to be true, I want an interval basically. So see, here for this node needs to be true, I want that this node should be lesser than 1, lesser than 1, and lesser than 8. So that is fine. Like if it is lesser than 1, then it's true. Okay. Now let's talk about this node, right? This node. So this should be lesser than 8, this node. Suppose if this is x, but it should be greater than 6. Okay, greater sign, sorry. Should be greater than 6. So basically, I am covering about the range, right? Let's talk about this 6. This 6 should be lesser than 8, but should be greater than 3, right? This node. So basically, I am finding an interval here, right? So I will start with the plus infinity and I will go till minus infinity. Now from here, basically in we will do in order traversal, right? I will first jump to the left node, right? I will come here and now see my value should be lesser than 8, right? My value should be lesser than 8, right? So that means on the negative side, let me put negative side here, just for our references. So minus infinity here, and plus infinity here. Okay. So here the values should be lesser than 8. So don't you think for this node, the values, the parameters will be changed, right? So basically my minimum is starting here with minus infinity and my maximum is starting with here plus infinity, right? Now here the values should be lesser than 8. So now this is for this node, the longest, or I will say it should be lesser than 8. So the range will it be, and I am taking an open bracket, so that means 8 is not covered here. So the range will be from 8 to minus infinity. Let me create it here. The range will be from minus infinity to 8, right? Because it cannot be greater than 8, it should be lesser than 8 only, right? Now I will come to here, then I will again come to the next node, left node in order traversal, right? Now the range for this will be minus infinity. Let me use only red pen. Minus infinity to 3, right? It should not be greater than 3. It should be lesser than 3, right? So it can go till minus infinity, but it should not be greater than 3. Now let's talk about this node, right? After left done, right? After left done, I will move to the right one, right? For the right one, what should be the range? Now it should be greater than 3. So if minus infinity will change and it should be greater than 3, but it should be lesser than 8, right? So you can see 8 is coming alongside here, 8 is changed to 3, more lesser, but minus infinity coming alongside, right? Now again, we will move to the left side, right? So for this, it should be lesser than 6, right? So now not lesser than 8, lesser than 6, but should be greater than 3, right? It should be greater than 3, lesser than 6, and here 2 is not in this range. 2 is not in this range. So what I will do, I will simply say return false. I will say return false. But let's explore more option. So I will come to here, right? This should be greater than 6, right? So the lowest point possible is 6, but it should be lesser than 8. So 6 to 8 is the range, and yes, 7 is lying in between them. For this, right, once this is done, right, I will come back, here, I will come back, then I will move for the right one. Okay, what should be the range here? It should be greater than 8, right, but less than infinity. So greater than 8, but less than plus infinity. Again, now it should be greater than, there is no left node, right? So I am again going to the right node. It should be greater than 10, but less than infinity. Yes. Now again, from here, right, I am at left. Now what it will be the range? It should be lesser than 14, right, but should be greater than 10. So it should be between 10 to 14, right? So basically what will be our approach going to be? We'll simply traverse to each node, right? What we can do? We can do an in order traversal, simple in order traversal, and we will simply put our root dot val in a range, right? My root dot val should be in a range. So basically it should be lesser than my max, right? It should be greater than my min, right? This will be my condition. If this condition is not true, right? If this condition is not true, I will simply return false. Otherwise, if it is true, again I will do further, like I will go to each node, I will find out each node. So basically what we can do, we can simply create our two variables, min and max, and we will simply change it. We will change it, right, whenever we get the values. All right. So this will be our approach. Okay. In the next video, I will give you a code implementation of it. And then in the next video, we will do a dry run. Okay. So see you in the next video where I will show you a code implementation of this approach. Okay. So see you in the next video.